All right, let's dive deep into the Linux kernel. We're going to talk about its most fundamental resource, time. We'll get into the clocks, the timers, and all the little delays that make modern multitasking even possible. Have you ever really stopped to think about how your computer can be downloading a massive file, playing a video, and letting you scroll through websites all at the same time without just completely locking up? Well, it's not magic. It's actually this incredibly sophisticated system of clocks, timers, and really carefully managed delays, all run by the operating system kernel. So to get started, we really need to understand the fundamental rhythm of the kernel. Just like a musician needs a metronome to keep time, the kernel needs its own steady pulse to keep everything perfectly in sync. And that pulse has a name. It's called Hz. You can think of it as the kernel's heartbeat. It's a setting that decides how many times per second the system's timer literally interrupts the CPU. Each one of those interrupts is called a tick, and it's the absolute smallest unit of time that the kernel scheduler even thinks in. On most modern PCs, this is happening 1,000 times every single second. And with every single one of those ticks, a master counter called jiffies just goes up by one. It's been counting every single tick since the moment you powered your computer on. So if hertz is the heartbeat, jiffies is the grand total of all those heartbeats. It's the kernel's master clock, and pretty much every time-related thing is built on top of it. Okay, so let's say a program needs to pause for just 1 second. Now that we know about jiffies, the most obvious way seems pretty simple, right? Just watch the jiffies counter until it's ticked 1,000 times. But as we're about to see, the most obvious way is also the absolute worst way. On the left, you've got this thing called busy waiting. This is like staring at a wall clock, just waiting for a minute to pass. You literally can't do anything else, and you're just burning energy, watching. A busy waiting loop does the exact same thing. It eats up 100% of a CPU core just checking the time over and over. Now, a slightly better idea on the right is yielding. That's where the process says, hey, scheduler, I'm good for now, let someone else have a turn. The trouble is, it immediately gets put right back in line, constantly asking, is it my turn yet? Is it time yet? It's still incredibly wasteful. And this is not a small issue. I mean, as the source material says right here, this kind of loop can make the entire computer look like it's completely frozen. Because one selfish process is hogging the CPU to do absolutely nothing, no other real work can get done. So, yeah, we need a much better way. And of course, the kernel gives us a much more elegant and frankly brilliant solution. Instead of just waiting around, a process can tell the kernel, hey, put me to sleep and just wake me up later. This amazing approach uses a function called schedule_timeout. And honestly, it's just like setting an alarm clock. First, the process tells the kernel it's going to take a quick nap. Then it tells the scheduler exactly how long to nap for, in jiffies. The scheduler then completely removes the process from the line of tasks waiting for the CPU. It's totally gone. The CPU is now 100% free to do other useful stuff. Then, when the timer goes off, the kernel just puts the process back in line, ready to go. It's efficient, it's elegant, and it's the right way to handle delays. Okay, so sleeping is perfect for pausing a task. We've got that. But what about a different kind of problem? What if you need to schedule some code to run in the future, but you can't have the current program just stop and wait for it? This is where we get into the idea of deferred work. Just picture a device driver. When you tell it to do something, it might need to check on the hardware status in, say, a few milliseconds. It can't just put your whole program to sleep while it does that check. No way. Instead, it has to be able to tell the kernel, hey, could you run this little function for me in about 10 jiffies? And then immediately hand control right back to your program. So to solve exactly this problem, the Linux kernel gives us this powerful little toolkit with 3 main tools. Let's take a look at kernel timers, tasklets, and work use, and see how each one makes a different trade-off between pure speed and flexibility. First up, we've got kernel timers. These are perfect for a one-shot deal, something you need to happen at a very specific moment in the future. Now, the key thing to get here is that they run in this special interrupt context. You can think of that as an express lane inside the kernel. It has to run right away and finish fast. And because of that, it has one major rule. It cannot sleep. It can't do anything that might block, period. Next are tasklets. They also run in that same super fast, high priority interrupt context, which means, you guessed it, they can't sleep either. The big difference is you don't give them a specific time. You just tell the kernel, run this as soon as you possibly can.
That makes them fantastic for quick follow-up actions that need to happen right after some hardware event.
And finally, we have work queues. And these are the game changer. Unlike timers and tasklets, a work queue function runs in the context of a totally normal kernel process. And because it's a process, it has a superpower the others don't. It can sleep. This makes it unbelievably flexible for any task that might need to wait for something, like the disk or the network. Now, what's really cool about this slide is how it just lays out all the trade-offs so clearly. You can see timers and tasklets run in that software interrupt context we talked about, that fast lane. Work queues run as a regular kernel process. But the most critical, the most important row here is, can it sleep? That single word yes for work queues, well, that's everything. If your deferred task needs to do anything that might block, you have to use a work queue. It's that simple. It really shows you the kind of design choices kernel developers make every day. So, okay, we've gone from the kernel's tiny little heartbeat all the way to these complex deferred work systems. Why does any of this low-level stuff actually matter to you? Because these are the fundamental building blocks of a smooth, responsive computer that doesn't freeze all the time. So let's just recap the big takeaways. A kernel's entire world revolves around its HZ pulse and its Jiffy's counter. We learned that the simple, obvious way of busy waiting is a performance nightmare, and that the only sane way to delay something is to properly put it to sleep. And for all that do this later stuff, the choice between timers, tasklets, and work queues all boils down to one critical question: does my task need to sleep? Getting that one question right is what makes a system feel fast instead of frozen. And that really leaves us with a final, bigger question. This whole journey from a simple, dumb busy wait loop to a complex, powerful work queue system, it really highlights a constant trade-off in engineering. When is a simple but inefficient solution good enough? And when do we absolutely have to embrace complexity to get the performance and responsiveness we need? It's a question every single system designer has to answer. Thanks for watching.